Gosh. Welcome back to this class. So we are now in chapter 3. We are now discussing the actual combustion event that happens in spark ignited and compression ignited engine. I started my discussion on SI engine combustion, and then I will move on to CI engine combustion. In SI engine combustion, so far we discussed about the overview of the combustion process in SI engine. Today, I'm going to discuss about the different stages of combustion in spark ignited engine. So actually here we are characterizing the combustion event in SI engine in terms of number of stages. The idea behind characterizing the combustion event is we want to control this combustion event so that we could improve the engine performance and reduce the pollutant emission. We need to be familiar with the variables or factors that affect different stages of combustion. So towards that objective, we are first characterizing the combustion event in terms of number of stages. After this, we will discuss about the engine design and operating variables, which are designated as factors here. We will identify various factors that affect different stages of combustion. Identifying these factors will help us to have a control over the combustion event, okay, so that we can improve performance of engine as well as reduce the pollutant emission from the engine. So I started my discussion on this different stages of combustion in the previous class. Okay, so here there are two things. One is a theoretical P theta diagram, pressure crank angle diagram, which is also called pressure profile. So in a theoretical diagram, as we have discussed, the combustion event occurs instantaneously. You could see that the combustion event is constant volume combustion according to Otto cycle. That is a theoretical cycle to model the spark ignited engine heat addition. Okay, so it is modeled using Otto cycle, wherein the heat addition process is constant volume. So in a theoretical pressure crank angle diagram, I already said why we are analyzing pressure in crank angle domain rather than time domain. Time domain doesn't make any sense here because it completely misses out the information related to where the piston position is. That's why we are analyzing pressure variation with respect to crankshaft angular position. Crankshaft angular position is related to piston position inside the cylinder. Basically, we are analyzing how the in-cylinder pressure varies with respect to piston position. This is an important information. We need to know, or we need to track the piston position with changes in pressure. Okay, so that is important from the combustion analysis perspective. That's what we are doing here. In a theoretical cycle, you will have a vertical line. Entire combustion event happens at TDC. TDC is a reference point. I already said about this. TDC, piston reaches TDC, top dead center, twice during one engine operating cycle in a 4-stroke engine. Okay, 2 times the engine reaches top dead center, one during end of compression stroke and second time during end of exhaust stroke. We are not considering end of exhaust stroke, that is unimportant. What we are considering here is the end of compression stroke. When the piston reaches end of compression stroke, that is what is taken as a reference point. Because that is the region where the combustion event is happening. That's why we are considering this as a reference point. So in a theoretical process, heat addition happens instantaneously. Combustion occurs instantaneously when the piston is at top dead center. So you have a vertical line here. Before that, you have the compression event, where the charge is compressed, fuel or mixture is compressed, then heat addition is instantaneous. After that, you have an expansion process, okay, so wherein you are recovering work. So according to this theoretical diagram, the energy release is instantaneous, so you can recover maximum work, okay, during the expansion process if at all it happens in this way. So you will have maximum work extracted and thermal efficiency is also very high if at all heat addition happens this way. But we don't want this to happen in an actual engine. We don't want instantaneous combustion in an actual engine, although we know that this is going to give high thermal efficiency. This is going to increase the work output of the engine. So why we don't want this?
It's because of explosive nature.
So here instantaneous combustion is, as you rightly said, it is like an explosion. Right, you know how a bomb blasts. So it is in no time a large thermal energy is released. if large thermal energy is released, okay, so the magnitude of thermal energy release here depends on how much of fuel and air is combusting, right? When the fuel air quantity is more, then the thermal energy release is accordingly high. Okay, so the damage will be accordingly severe. Okay, when fuel air quantity is less thermal energy is released. Nevertheless, we don't want this instantaneous energy release because it's like an explosion. This is going to damage the engine. Okay, we don't want this to happen. We want to have a progressive combustion. We don't want instantaneous. What we want to happen in an actual engine is progressive combustion. That is what we are going to see here. Actual combustion event is progressive, as you could see here. It occurs gradually, not instantaneous. It occurs gradually. It starts here in A, indicated as A, that is start of spark discharge. It ends at point D. Okay, so you could see that there is a considerable period of time the combustion occupies. It is not instantaneous as shown in the theoretical diagram, where the entire energy release happens at TDC point, indicated as 0 degree here. Please also note the crank angle nomenclature that I have followed carefully. On the left-hand side, you could see that I have indicated crank angle with a negative sign. On the right-hand side, I have indicated crank angle with a positive sign. This is a standard nomenclature. During the compression stroke, when the piston is moving up, when the piston is yet to reach the TDC point, so this is TDC point. During compression, piston is moving up. During expansion, piston is moving down. So this is expansion is always considered as positive crank angle, and compression is always considered as negative crank angle. I will later on tell you the reason. Okay, but this is a standard nomenclature you need to note down. So here I have a negative value, here I have a positive value when I indicate the crankshaft angular position. And this is my reference point. So this reference point 0 degree is TDC point, compression TDC point. I have two profiles here. One is motoring, the other one is firing. So this is a motoring profile indicated in the not continuous line, breakup line, and this is a continuous line, which is a firing pressure. Firing pressure is in continuous line. Motoring pressure is the other one. What is motoring pressure? Any idea?
Without ignition.
Without ignition. So motoring pressure here is uptime without ignition, meaning without spark discharge. So this is without spark discharge. So if you run the engine without discharging electric spark, there is no combustion at all. There is no ignition, there is no combustion. So you will get a profile, P theta profile, something like this. This profile is motoring profile or motoring pressure profile, and the other one is with spark discharge. Once you discharge electric spark, that is a combustion event. With combustion event, you will get a profile indicated here as a firing pressure profile. Okay, so these two profiles are overlapped here. There is a reason behind this. This helps us to identify the different stages of combustion. So now we are going to see the different stages of combustion indicated using this motoring pressure and firing pressure profile. I have also used two other profile to identify the different stages of combustion. One of the profile is called mass fraction bond profile. So here in y-axis, you have mass fraction bond X with a subscript B. What is mass fraction bond? That is written here. XB is equal to MB divided by MU plus MB. What is this MB? MB is mass of the bond charge. MU is mass of the unbound charge. So what you have in the denominator is the total charge, bond plus unbound. What do you have in the numerator? You have the bond charge. That's why this is indicated as mass fraction bond. It's a mass fraction. Okay. With respect to total mass, how much of mass is bond? That is what is mass fraction bond, XB. So XB is in y-axis, and in x-axis you have theta, crank angle. So you will get a, when you plot the mass fraction bond profile with respect to crank angle, you will get a profile like this. Okay. In this profile, you can indicate the three stages of combustion. Okay, indicated here as stage 1 is this, and indicated as A here. Stage 2 is indicated as B here, and stage 3 is indicated as C here. Okay, and during stage 1, okay, around 10% of the charge is burned. So here mass fraction burned is represented in percentages. Okay, so 10% of the charge is burned here. The corresponding crank angle duration is stage 1. During the second stage, that is B, okay, almost 80% of the charge is burned. So in total, already you have 10% bond. So 10 plus 80, 90%. So this duration or period is the second stage, indicated as B. Third one, during the third stage, the remaining 10% of the charge is bond, as you could see here. So that is indicated as C. This is again 10% of the charge is bond, okay, during stage 3. There is another plot I have shown here. On x-axis, what you have is flame travel distance. On y-axis, you have flame travel distance. On x-axis, you have flame travel time. This is time and this is distance. When you plot flame travel distance versus time during the combustion event, you will get a profile like this. And you could see that this profile is exactly same as what you have observed here in the mass fraction burn profile. So mass fraction burn profile and this profile are exactly same. Okay. Now, what is the slope of this? What is the slope of this line? So when you take a slope of this flame travel,
Pressure per angle.
what is that?
Flame velocity.
Flame velocity. Exactly. So this is D. This is time T. Slope is nothing but this is flame velocity. Now, how do you get this flame travel distance versus time? So this is obtained from optical engine. Okay, so you could see here that these images are taken from optical engine. Okay, we do research, a lot of research on metal engine as well as optical engine. In an optical engine, you could take images of the combustion event, okay, at different instant. Time is indicated in crank angle. Here it is 3 degree, 4 degree, 6 degree, and 8 degree. So at different crank angle instant, you could see here how the flame moves, flame propagate across the combustion chamber. Okay, so I have earlier given an overview of the combustion event wherein the flame get formed around the spark plug location and then start to move or propagate across the combustion chamber. And the overall combustion event is a flame propagation based event. So if you have an optical engine, you can track the distance moved by the flame with respect to time. Flame is formed in this region and then start to move. Okay, with respect to time indicated here in terms of crank angle, the flame is moving away from the spark plug location. So you can track the distance moved by the flame with respect to time. That is how you get this profile, third profile, that is flame travel distance versus time. That is associated time for the distance travel. That is how you get this profile. The slope of this is nothing but flame velocity. Okay, so earlier when I have provided an overview of SI engine combustion, I said the overall combustion event is flame propagation based event. The flame moves at some velocity indicated as normal flame velocity. It's a velocity of the flame in a direction normal to its surface. That is what is normal flame velocity. So the combustion event in SI engine overall, it is indicated as a flame propagation based event. The rate at which the flame moves will govern the rate at which the thermal energy release. So flame velocity carries a lot of significance. The slope of this diagram provides that. And you could also observe that if you mark the stages of combustion here, similar to what you have done in the mass fraction burn profile, that is previous profile, if you could mark the 3 stages of combustion, so you will get something like this. So here you could observe clearly the change in slope. For stage 2, the slope is larger. Stage 3 and stage 1, the slope is very low. Okay, the slope of the profile is very low for stage 1 and 3, whereas for 2, it is considerably high. This is higher value of slope and this is lower value, this is lower value. Meaning at stage 1 and stage 3, the flame is moving at a lower velocity, whereas in stage 2, the flame is moving at a higher velocity. This is again an important inference for you to note down when you analyze the different stages of combustion. Now, coming back to the first plot which shows motoring and firing pressure profile. Here, let us look at the different stages, right? How do I identify these different stages of combustion? Point A here marks the start of spark discharge. So this is where the electric spark is discharged by using a spark plug. Okay, by using a spark plug at this instant, at this crank angle instant, you are discharging electric spark. Okay, so stage 1 starts here at A, and stage 1 ends here at B, right? How do I identify B? From the profile, can you tell me how this B is identified?
Where the so spark is flame is like established and is rate of pressure rise.
Ignition.
Rate of
Start
pressure
of
rise.
ignition.
Where ignition pickups means compared
Start of
to
ignition.
motoring curve.
Yes, ignition pickups when compared to motoring pressure, and Roshan, you said rate of pressure rise is different. Okay, so the important point here is this: until point B, you could see that these two profiles just overlap over each other. There is no considerable difference between the motoring pressure profile and the firing pressure profile until point B. At point B, you could see that the firing pressure profile start to deviate from the motoring pressure profile. So motoring pressure is going like this is going like this. So you could see the deviation of firing profile from the motoring profile at point B. So that point is taken as the end of stage 1. So stage 1 is indicated here as a flame development period. So there is a considerable period of time taken to develop a flame. So it's not about forming a flame. You need to ensure that the flame formed is self-sustaining. Okay, otherwise the combustion event cannot continue. So you know that in an engine, real engine also, we often encounter this misfire cycles, right? Misfire cycles. Have you come across this term, misfire cycles?
Yes, sir.
So often you come across this term in SI engine terminology, misfire cycle, meaning that you are discharging electric spark, but the combustion event is missed. Few cycles are missed. Why? Because we don't have a self-sustaining flame. The flame is not stable. You are discharging electric spark, you are trying to form a flame, but the flame is not a stable flame. That's why you end up in misfire cycle. So stage 1 ensures that we are forming a self-sustaining flame, and that is happening around the spark plug region. Okay, that is happening around the spark plug region. It starts with the spark discharge. It ends at the point where the firing profile deviates from the motoring pressure profile. So at this point of time, as indicated in the mass fraction burn profile, around 10% of the charge, 10% of the total charge. When I say charge, it is fuel plus air. Fuel plus air is indicated as charge. Around 10% of the charge, 10% of the charge is burned during the first stage. Now let us get into the finer detail, see what is happening. So what we have here, as you could see here, there are two electrodes, right? There are two electrodes, and the gap you have is called the electrode gap between the two electrodes. There is a small gap which is called electrode gap. Generally, it is less than 1 mm. It varies anywhere between 0.7 to 1.7 mm. It needs to be optimized. Later on, I will talk about this. So you have a small gap between the two electrodes, and that is the region where you have fuel air mixture. So you are containing a small volume of fuel air mixture within an ignitable range. Recollect what I have said during the overview of SI engine combustion. Combustion cannot get started until you have a proper combination of Phi and T. This you should always remember, right? If any one of this is missing, there is no combustion. So to initiate combustion, you are discharging electric spark, you are giving T ignition, but what you also need is Phi ignition, ignitable charge. So we have a small gap between the two electrodes. In that gap, you have a fuel air mixture within an ignitable range. You are discharging electric spark to this mixture, T ignition. Because of this combination, you are forming a flame around the spark plug region. Okay, so in terms of some specifications related to how much of energy we are discharging here, the voltage that you discharge can vary anywhere between 25,000 to 40,000 volts. 40,000 volts, that is the voltage that is discharged during, with the help of spark plug. The current rating is around 200 amps. Okay, and this discharge of electric spark is done for around 10 nanoseconds. 10 nanoseconds, 10 power minus 9. Okay, so 25,000 to 40,000 volts with 200 amps current discharge for 10 nanosecond. Okay, and you get into forming this spark as indicated here, electric spark. Okay, in terms of energy, this is around 30 to 50 millijoules. That is the energy you are discharging through the spark plug. What you need to ignite the mixture is only 3 millijoules. To ignite a hydrocarbon air mixture, P ignition, hydrocarbon, the fuel we use is hydrocarbon fuel. For igniting hydrocarbon fuel air mixture, you need 3 millijoules of energy. Instead, you are discharging 30 to 50 millijoule, more than 10 times of thermal energy is discharged. So basically, this mixture contained within the electrode gap is offering a resistance to this high voltage and current, and this resistance, thermal resistance, reflects in the form of a spark. That is what you are seeing here in the second picture. So the flame gets, the spark gets formed because of the resistance offered by the mixture that is contained between the electrode gap. Okay, and that is what is discharged in terms of thermal energy. In terms of magnitude, it is around 30 millijoules. Although you need only 3 millijoule, we are discharging a very high thermal energy. What could be the possible reason for this? Why we are discharging 10 times higher?
Safety, sir, mostly.
What is it?
It's a factor of safety, so it we are not missing any. Like if we are having edge-to-edge condition, probably sometimes the spark energy will not be sufficient to ignite the mixture.
The primary consideration here is we want to form a stable flame.
Right.
But what could be the reason for high factor of safety? We are discharging 10 times or more energy than what is required. Anything you can think from the heat?
AFR can vary, sir, in that. Sorry.
What is it?
Sir, fuel air mixture availability around the spark plug. That will vary from cycle to cycle to ensure that the flame is getting ignited in the worst case condition also. Hence, the factor of safety is kept high. That is my understanding.
So you mean to say that the Phi ignition, that fuel air proportion varies?
It might vary, sir, from cycle to cycle. Not significantly, sir, but in some conditions like.
So that is a different phenomena. I'll talk about it. You are talking about cycle to cycle variation in the Phi value. That is obvious in a SI engine. I will talk about it. But here the question is we are discharging 10 times or higher thermal energy than what is required to ignite the mixture. And
so the quality of air maybe?
Quality of air, okay.
Sir, to overcome carbon deposition.
To overcome carbon deposition, okay.
To accelerate the process.
To accelerate the process. To accelerate the flame development process.
Right, sir. Yes.
Okay. Anything else? What will happen to heat loss? The major factor you are missing out, all of you are missing out, is heat loss. So in this region, around the spark plug region, initially fuel and air are at a lower temperature, right? You are inducting air at an ambient condition. Air and fuel are typically under ambient pressure and temperature condition. If the surrounding ambient temperature is very low, then accordingly the temperature of the mixture is considerably low. When you have a lower temperature air fuel mixture, the heat loss from the spark plug region is considerably high for two reasons. One, fuel air mixture is at a lower temperature. Second reason, the spark plug electrode initially will be at a lower temperature. This metal elements are at lower temperature. So you will have considerable heat loss happening from the spark plug region. The heat loss is considerably high. Okay, because of that, the flame may not get sustained. The ignition will happen, the flame may not get sustained because of the very high heat loss. This is the reason why we discharge high thermal energy 10 times or more although there is a heat loss, we want to overcome that. We want to ensure that we are forming a stable flame. This is exactly the reason why we are giving a very high thermal energy than what is required. Primary reason is the heat loss. Okay, the other factors will also play a role, as you said, but the primary factor or a significant factor is a considerable heat loss from this region for two reasons. One, fuel air mixture is at lower temperature, and the spark plug electrode initially are at a lower temperature. So you will have a considerably higher heat loss happening in this region that may quench the flame, quench or extinguish the flame. We don't want that to happen. That's why we are discharging very high thermal energy. We ensure that a stable flame is formed. So stage 1 is concerned with forming a stable flame around the spark plug region. Once the flame forms, stage 2 is what is happening once a stable flame forms. So stage 2, as indicated here, is called flame propagation period or rapid burning period. Why it is called rapid burning period? You can infer from the mass fraction bond profile. Almost 90% of the charge is burned. It starts at 10% and it ends at 90% of the charge. So in total, you are burning 80% of the total charge during the second stage. That's why this stage is also referred to as rapid burning period. Okay, where most of the charge, 80% of the charge is burned. When do it start? It starts in B and it ends here C. So 80% of the charge generally is burned after the occurrence of the P max. So this is maximum pressure. After the occurrence of this maximum pressure, the stage will come to an end. That is marked as C here in this profile. Okay, C marks the end of stage 2. So what is happening if you look at during stage 2? The flame, stable flame formed around the spark plug location start to propagate across the combustion chamber. Okay, across the combustion chamber, it moves at a faster rate, and that during its progress, during its movement across the combustion chamber, as I said, around 80% of the charge is burned. 80% of the charge is burned. That's why it is called rapid burn period. So the flame velocity plays a significant role here. We want the flame to move at a higher velocity so that the burn rate is high. Right? We already discussed about what are the factors that affect the flame velocity. If you recollect, when I have provided the overview, I said there are physical factors, there are chemical factors. Chemical factors are kinetics governed by fuel molecular composition. Physical factors are heat transfer, mass diffusion, and fluid dynamics based on how you design the combustion chamber. So all these factors affect the flame velocity. And based on the flame velocity, the flame movement is going to be different. Okay. So we want a higher propagation speed so that most of the charge is burned. Again, it's not instantaneous. We want progressive combustion, but it should not be too low also. So flame velocity plays a major role here in affecting the rate of thermal energy release. Okay. So one of the important factors when we talk about flame velocity is, as I said, the flame divides the combustion chamber into two zones. What is behind the flame are burned gases. What is ahead of the flame are unburned mixture. So you have burned gas, which are products of combustion behind the flame front. What is ahead of the flame front? Unburned mixture, fuel air mixture. Okay. So you have two zones here. This burned gases, you know, they are at considerably higher temperature, and the unburned mixture is relatively at a lower temperature. Because of higher temperature, the burned gases are at lower density, and this is at a higher density. Okay, because of the considerably lower density, the burned products will try to expand and occupy as much volume as possible. So it means these gases will expand, try to occupy as much volume as possible. In the process, it will push the flame to move ahead. Okay, so it will push the flame to move ahead, and the flame moves at higher velocity. When the flame moves, it is also compressing the unburned mixture. So it means the flame movement is compressing the unburned mixture. So the pressure and temperature of the unburned mixture will start to rise. The other thing that happens during this period of time is flame radiate thermal energy, because flame is at a very high temperature, generally around 2000 K or above during the combustion time. So this flame zone or reaction zone will be at a very high temperature. So heat transfer occurs in all three modes. Radiation mode is significant because of the less available time. You know, conduction and convection takes more time, radiation takes lesser time. So radiative mode of heat transfer is significant during the flame movement. The flames start to radiate heat. So overall effect is the unburned mixture pressure and temperature start to build up. You know, kinetics will be increased when the temperature or pressure is increased. So that is why the flame movement happens at a faster rate, because kinetics start to happen quickly. This unburned mixture is subjected to progressive increase in pressure and temperature. This will allow the flame to move at a higher velocity. That's why almost 80% of the charge is burned during this period of time. One of the most important event that happens during the second stage is, you could see that the maximum pressure is happening during this period of time. And you know, the magnitude of maximum pressure affect the power output from the engine, torque or power output from the engine. So we want to ensure that we have a maximum value of the pressure so that you can recover that in terms of work, useful work in the engine. So the torque and power output largely dependent on this maximum pressure value. It also depends on the occurrence when the maximum pressure is happening. Okay, as I already told you, untimely energy release is of no use. So we have to time it appropriately so that you can recover that into useful work. So the magnitude of Pmax plays a role, and the occurrence when the Pmax is happening also plays a role in affecting the maximum power output. And this is happening during the second stage, where most of the thermal energy is released. Okay, then we have the final stage marked as CD. This CD is stage 3. Stage 3 is referred to as flame termination period. This is also called the after burning period. So during this period of time, the flame gets terminated. That's why it is referred to as flame termination period, also called after burning period. During this period of time, the flame will reach the extreme corners of the combustion chamber, where you have solid boundaries. The flame will be near the boundaries or the corners of the combustion chamber. Because of this, the flame velocity will get reduced, because you have a dampening effect given by the solid boundaries. So the flame velocity is considerably reduced. And you could see here that the most of the flame will be in contact with the solid boundaries, and very little surface is in contact with the unburned mixture. So here we are talking about the unburned mixture that are residing here in this location, in the corners. So this has to be burnt by flame ignition. Okay, so the flame will move at a lower velocity because of the dampening effect. The flame is in contact with the solid boundaries, so heat loss will start to increase. Okay, and lesser flame surface is in contact with unburned mixture, through which ignition is happening, right? And the unburned mixture will start to burn slowly. So this process happens generally at a slower phase, primarily because of the less flame velocity. You know, flame velocity is what is governing the rate of thermal energy release. During the third stage, it is considerably less. Velocity is considerably less. That's why the mixture is burned slowly during the third stage. So, so it happens slowly. Around 10% of the charge is burned during the third stage. So you will eventually reach a condition where the heat loss from this region, flame region, is higher or equal to the heat that is released from the flame. When that situation happens, what will happen to the flame?
It will start emitting, sir.
Quenches.
Flame will quench. It's called flame quenching. So that marks the end of the combustion event. Flame will get quenched. Okay, when the heat loss from the flame zone start to dominate. When this increases, there is something called heat release, and there is something called heat loss. When these two get balanced, the flame will get quenched. That marks the end of the combustion event. Okay, that is what is the third stage, which is called flame termination or after burning stage. So in the mass fraction profile, you could see that the remaining 10% of the charge from 90 to 100, remaining 10% of the charge is burned during this period of time. That is stage 3, marked as C here in the mass fraction burn profile. Okay, remaining 10% of the charge is burned. Now, as I said, the slope is considerably different. For the second stage, it is considerably high. Stage 1 and stage 3, it is considerably low. Slope is considerably low, meaning flame velocity is high only during the second stage. First stage and third stage, flame velocity is very low. Especially in the first stage, it will be almost like a flat line. Okay, the flame velocity is considerably low. That is what you want to form a stable flame. Okay, in the last stage also, since the flame has reached the corners of the combustion chamber, the slope is less, meaning that the flame velocity is less because of the dampening effect of the solid boundaries. The second stage, the flame is in the core region of the combustion chamber where it propagates at a very high velocity, burns almost 80% of the charge during the second stage. Okay, so this is how the different stages of combustion are happening in a spark ignited engine, actual spark ignited engine, that is identified with the help of this pressure profile, motoring and firing pressure profile, which is also identified with the help of the other two plots. One is mass fraction burn profile and the other one is the flame velocity profile, defined in terms of flame travel distance and travel time. Right? As I said, the purpose of characterizing the combustion event in terms of number of stages is that, so we want to control this combustion event effectively to improve engine performance and reduce pollutant emission. That's the reason why we have characterized the event in terms of different stages. Later on, we will identify the factors that affect each of these stages. Okay. Now here, when we discuss the second stage, one of the important information is the Pmax, the magnitude of Pmax, and when this Pmax happens in a typical SI engine. This is primarily controlled based on when you are discharging electric spark. So this is under your control. So in engine, you know, you have a ECU, electronic control unit. Based on operating condition, the spark discharge time has to be optimized. We use the word optimal spark timing. Okay, so we want this timing to be optimized so that you can get the maximum power output. Towards that, there is something called MBT timing, which is maximum brake torque timing, or in some literature, it is also indicated as minimum spark advance to get the maximum brake torque, which is what is the MBT timing, which gives you the maximum torque. Okay, that is indicated here with pressure profile. As you could see here, there are 3 pressure profiles here marked, and these 3 pressure profiles are obtained with 3 different spark timings marked as A, B, and C. So you have 3 timings marked as A, B, and C. Okay, so you have 3 different timings, and one is called advanced spark timing, second one is optimum timing, and third one is called retarded timing. Now, how do I identify this 3 timing with respect to piston position? So this is the reference is always compression TDC. This is A, this is B, this is C. Okay, so this A, B, C are the different spark timing. This I indicate as advanced spark timing. This is optimum spark timing. Third one is retarded spark timing, meaning that when I discharge electric spark for KCA, if you consider KCA, when I discharge electric spark, the piston is at this position. This is what I mean by, this is what I mean here, because when I discharge electric spark, right, with the advanced timing, the piston position is this. Similarly, when I discharge electric spark for case B, the piston is here. For case C, the piston is here when I discharge electric spark. So you have 3 different cases. And this is indicated as advanced timing because the piston is far away from the TDC point. That's why it is indicated as advanced timing. Case C is where the piston is very close to TDC. This is generally indicated as retarded timing. Retard means delayed timing. This is advanced timing where the piston is far away from TDC. Retarded timing is when the piston is closer to top dead center position. In between, you have an optimal timing. It's between KCA and KC. Now let us look at when I discharge electric spark at this 3 different timing. Let us look at how the pressure profile is varying. This is what I am seeing here. When I discharge electric spark at I will have a pressure profile something like this. Okay, this is my P max. Then if you look at the second case, optimum timing, the pressure profile will be something like this. So this will be my P max. This is for A. This is for B. Now KC is here. I'm discharging electric spark here. I get a profile something like this. This is my P max for KC. Okay. Now which one you want? Case A, B, or C? You are controlling the spark timing, right? You are controlling the spark timing. Which one you will go for it? A, B, or C?
We will go for A if we are meeting the emission.
You will go for A.
Yes, sir.
Why you want A?
We will have a better efficiency.
Better efficiency. On what basis you are saying this will have better efficiency?
Because of pressure rise per angle is more.
Oh, you are saying that this pressure rise rate, this is more. Okay.
Yes.
Any other answer?
Sir, B.
B. Why B?
Complete combustion will happen. Percentage of burn rate will more compared to A.
Okay. On what basis you are saying this?
Combustion duration is more, no, sir, from our main injection timing to TDC to that peak.
So you're saying that from B to peak value, the duration is longer.
Yes,
And
yes,
this will ensure complete burning.
yes, sir. Yes.
You need to recheck. Longer duration doesn't mean that there is a complete combustion. Okay. Complete combustion and combustion duration cannot be correlated well. That's what I'm saying. Okay. So we cannot say that when the duration is more, there is a complete combustion. Even with more or longer duration, you may have incomplete combustion. Okay. That is something else you need to think here. Okay. But your answer is B. Any other answer?
Sir, answer, in my opinion, answer should be B only, because it will give the
B
best
only.
balance between the performance and NVH character, and I would say emissions also.
Why do you think B gives best performance?
I would say, sir, best compromise, sir. Best like basically the Pmax is high. That is ideal condition for getting the
But
maximum
compared
output.
to A, Pmax is less, right, for B?
Yes, sir. But
Loss of
sir,
off.
right, sir. But if the Pmax is high, it might give beyond a point. It might give harshness to the engine. That is point
Harshness
number
to the
one.
engine.
Yes, sir. That is point number one. Point number two. If
Now
the
let
Pmax
us
is
not talk about vibration or harshness. That is a different area by itself. Now we are looking at only from a process perspective. I want to get maximum torque. I'm looking at this 3 timing. I want to pick one timing that gives maximum torque. Let us, for time being, let us not consider the harshness or vibration here. Only from the torque perspective. I want maximum torque. I need to pick a timing.
Sir, basically, in my opinion, the timing B will give the maximum. What I mean to say, torque also, because if you look at, sir, it is just is little far away from the TDC. So mechanical advantage means when the pressure is acting on the piston. So the torque that arm radius which is available for us, the P into R, which will give the whatever is relative pulse to, thrust to the piston. That will be perfectly, I would say, in sync with the giving the maximum torque in that sense. Because if we are like firing near TDC, sir, the Pmax is just occurring at what I mean to say is at TDC, the crank is completely straight. There is no mechanical advantage left over there. And if you go far behind, then pressure value will decrease, so it will offset in that sense. That is my understanding, sir.
So you are talking about the crank position with respect to Pmax. If it is at TDC, you are saying that there is no moment. Because
there is no moment, sir. You're right, sir. So
I think you need to visit this, because this is nothing. Anyway, the crank is connected well with the connecting rod, right? Connecting rod and crank are well connected. It doesn't matter where the piston lies, whether it is TDC point or whether it is vertical or angular, it doesn't matter. Anyway, moment is going to happen. Okay, moment is going to happen irrespective of the piston position. Crank arm and connecting rod are well connected. It's going to create a moment irrespective of whether it is vertical or angular. That point you need to revisit. Okay, there is something else you people are missing. I'm trying to get that. B is fine, but is there something missing?
Sir, to generate a torque, we need to have a vertical pressure. Vertical force. Like if we are going away from the from the center of the crank, we will have vertical component of the force larger. So. I think that is the thing Roshan was mentioning, right, Roshan?
Yeah, Professor got the point. I think it's not the case actually.
I'm now no. You are again looking at design perspective. What I am again trying to address, Roshan and you, is that is perfect. Reciprocating engine design is well established. There is no, element of doubt in whether I will get a torque or not based on the piston position. Okay. So you are going to have it, but something else you people are missing, which I am trying to get from you.
Sir,
by just looking at the profile.
Sir, if you want to generate more torque, means we have to put more amount of fuel. This time duration, maybe for mixing purpose, air fuel mixer, it will improve because of that.
Sir, maybe one reason that flame propagation, if we advance the spark timing, we get time for flame propagation.
Okay. Okay, so what is missing is look at the three profile, A, B, and C, three timings. You see
area
this
under the curve, sir. I'm sorry, just last chance. If I'm trying to, like, area under the curve, will be maximum under the, what I mean to say, point B.
Area under the curve is no, area under the curve is more for A, not for B.
It will sharply fall down, let's say, if I'm not wrong. It will go gradually and then settle down. What I mean to say for the point number B.
But P max is high, right? That effect is more dominant.
Okay, sir. Okay, sir.
So what is missing is you just look at the slope of the three profile. So this is KCA, right? The slope is considerably high. Case 2, slope is relatively less. Case 3, slope is much lower. Okay, so slope is varying in this order. And when you look at when the combustion event happens, when I discharge electric spark in A, I am getting a P max value very high. This will translate into work, no doubt about that. And the P max is also happening early in the expansion stroke. So I have a larger magnitude. I am also having that magnitude happening early during the expansion stroke, meaning I can recover more work for KCA. But what problem I have with KCA with advanced timing is, since the combustion gets started early here, during the compression stroke, whatever work done by the piston during the compression stroke is called negative work. Because we are supplying work to the piston. Only during expansion, the work is positive, meaning work is done by the gas on the piston. During rest of the period, work is done by the piston on the working fluid, in this case, gas. Okay, so compression period, whatever work you give to the piston, that will increase, and that work is indicated as negative work, that will increase when the combustion gets started earlier. You just look at the slope here, the rate of pressurize is so high. Once the combustion gets started, the high pressure, high temperature gases, okay, piston is moving up. Once the combustion gets started, the gas pressure will be significantly high. This is trying to push the piston in the downward direction. The piston has to move continuously in the upward direction for compression, okay? But the gases expand and try to push the piston in the downward direction. piston is doing more work now against the expanding gases when the combustion gets started earlier. So ultimately, what is happening with advanced spark timing? Negative work increases considerably. Negative work increases considerably because piston is doing more work against the expanding gases. Now you look at the case C. Case C, the problem is you have a retarded timing. Pmax is considerably low. Pmax is considerably low. The work you can recover during the positive work that you can recover during the expansion stroke is considerably less in case of C because it is dependent on the Pmax value. For A, Pmax is high. I will recover more work, but the problem is I'm also doing more negative work. This is also high with case A. With case C, this is considerably less. B is a compromise between these two. What I am trying to say is when I say optimal, this optimal is a compromise between optimal timing is a compromise between decrease in negative work, loss of expansion work. Two things are happening here. When Pmax magnitude is less, when the Pmax occurrence happens away from top dead center position, there is a loss of expansion work. Okay, that is happening with B. But what is also happening with B is the negative compression work is considerably less. Negative compression work is considerably less. Overall effect is the work, useful work that I will extract is higher only for case B, not for A, not for C. Why not in C? Because Pmax is less, so there is a loss of expansion work. Why it is not happening with A? Although Pmax is high, the problem is the negative work is considerably high with case A. Okay, that effect is more dominant, so your useful work is going to be lower because of this effect. B is a compromise between these two. That's why you get a better work extraction for case B rather than case A or case C. Okay, it's time up. I stop here. If you have any questions, I can take it.
Sir, just for knowledge purpose, like sir, this profile you said that selection of this profile, is it experimental based or sir we can do the simulation for this?
Experimental. You can discharge electric spark at different time and you can get the experimental pressure profile. It will be something like what I have shown. This what I'm saying here is this profile you can get from the experiments.
And sir, for actual engine also it is done, means the spark timing that is given experimentally only, sir. Like, I mean.
Yes, you can control the spark timing. You have a control unit. Okay, you can fix the timing for spark discharge. It can be A, B, or C. You can do a spark timing sweep. At a different timing, you discharge electric spark for the same load condition and check how the profile is coming.
And sir, this spark is given for how many degrees, sir?
How many degrees in the sense? Spark, you are talking about time for spark discharge. I said nanoseconds, 10 nanoseconds.
Oh, okay, sir. Okay.
10 power 9 minus 9 second, 10 nanoseconds. That is the duration of spark discharge. Okay. That's why energy is less. Although voltage and amps are high, energy is less. Okay, energy is joule per second. That is watt into second. Second is 10 power minus 9 nanosecond. That's why you get 30 to 50 millijoules.
Understood, sir. Means high amount of spark just for a fraction of second.
Yes, nanosecond.
Understood, sir. Thank you so much, sir.
Fine.
Hello.
Yes.
Sir, you know this side. Sir, I joined at 6:03 p.m. Sir, I think you marked me absent. I was saying present, but after that you started the class.
Okay, you joined late.
I joined at 6:03, sir. Actually, just 1 minute late.
Okay, fine. I have
Sir.
Yes.
Yeah. So we have this query regarding quiz one. So me and Roshan, being in the same company, we decided to attend, write the exam from the company premises, where we have a conference room, or we can sit in the place where we attend the classes. So means we just wanted to know how the question papers will be shared and how the answer sheets.
Question paper will be shared to your email ID, official email ID. Okay.
Okay, sir.
I should not use personal email ID. I will share the question paper to your official email ID. That is where I am communicating every day, right? Same email ID I will use. Using that email ID, I will send the question paper to you few minutes before the start of exam. Once you write the exam, you have to scan your answer script and send it to me. Send it to me in the same email ID from where you received the question paper. I will also give the detailed instruction just before the exam, okay, what you have to do. But this is in a nutshell, this is what you are doing. I will send the question paper to your email, and after the exam is over, you scan the answer scripts and send it to me. E-copy of your answer script I will receive after your exam.
Right. Okay.
I will correct and send it to you, same e-copy. For rest of the people, it is hard copy. I will correct the hard copy. Whenever you are coming to IITM, you can get the hard copy of the answer script.
Sir,
Okay, sir.
assignment,
And regarding the camera, sir, means is this camera what we are seeing right now?
Yeah, only
is
thing
it
is
okay
you
or
cannot
do we,
go ahead.
yeah? Is it okay or we need to have some conference room where
This is
we have
okay,
a
but
camera?
your background should be natural. You cannot have a blurred background.
Right. Okay.
Okay.
Professor, I have a question. Right,
Yes.
like suppose if we have a like a blended fuel, like what I meant to say is like isooctane is mixed with alcohol. It's ethanol. Sorry, I'm sorry.
Mm-hmm.
So the chemical equation for the stoichiometry, like 30% of the fuel is 30% of ethanol is mixed with 70% of some like C6H14, something like that. Then
Okay.
if you try to write the equation for a stoichiometry,
Mhm.
and so can I write like 0.3 multiplied by C2H5OH plus 0.7 multiplied by C6H14 plus alpha plus beta divided by 4 into O2 plus NO2 and N1, N2, whatever.
So whatever fuel you blend for the stoichiometric equation, for writing the stoichiometric equation, what you need is just CH. If at all oxygenated, it is O. It doesn't matter. The model doesn't know whether you have a blend fuel or you have a single component or you have a multi-component. From the model point of view, what you need is just a formula. You arrive at the formula, get the number of carbon, hydrogen, and oxygen, write the equation. That's it.
So there is no need of writing like 0.3 of C2H5.
No, you can do that calculation to get the number of carbon, hydrogen, and oxygen atom. That's it.
Oh, I got the points. So basically,
Once you get it, you write the equation only with CH and O. If at all it is
Okay, so-
oxygenated, if not CH alone.
I got the point. So basically, suppose if 30% of ethanol is mixed with 70% of what I meant to say is C6H7, then I can have an empirical formula derived for the what I meant to say
Yeah.
blended fuel, and I can write that as a stoichiometric
Yes.
equation, right, sir?
To write the combustion equation, you need to know the fuel formula. Whatever you do, you get the formula. If it is a blend, you do outside calculation, get C, H, and O, write the equation. What you need
Got
for
it.
the model is only formula. That's it.
Thank you, sir. Thank you. I
Because
got it.
model don't know whether you have a blend fuel or a single fuel or a multi-component fuel, right? From the model perspective, we have to just get the formula for the fuel. That's it.
Noted, sir.
Yeah.
Thank you so
Okay.
much.
So it's time up. I stop here. I will see you tomorrow.
sir, the assignments we have to submit your S-mail account, sir.
Yes, mail account.
Okay, sir. Thank you.
I had an email today. I have some problem. I have missed out to inform you. You can send it to my S-mail. Today I have sent an email, right? Same email. Please submit your assignment.
Okay, sir. Thank you.
Okay. Thank you.
Sir, Yadav is here. Sir, I'm in Pune, so I'll do my this quiz from my home. Would it be okay?
Yeah, wherever you are, you show that you have a stable internet and you should switch on the video, right?
Okay.
And then
Yes,
take the exam.
Okay. And sir, in the last session, you mentioned that if we have any planned leave, so we should inform you on mail.
If you are not attending the class, just inform me over email. That is enough for my record. Okay.
Okay. So, sir, on 11th March, probably I will not. I'll be absent on the class, so I'll put in a mail
Okay.
because I have marriage that day.
Fine. Okay. Your marriage.
My wedding is there on 11th March.
Oh, you are getting married. Okay. Congratulations. My hearty congratulations.
Yeah. If we can postpone that lecture, that would be very fun for me.
No, actually, case by case, if I postpone, it will become a problem in meeting the schedule, time schedule. Okay, so you can check with your friends for the lecture notes. Okay, and if you have any doubt, you can write to me. There is any doubt on the lecture that is covered on that day, you can write to me.
Will work.
Okay. Thank you. So I stop here. I will see you tomorrow at 6 o'clock. Thank you. Bye.
Thank you, sir. Thank you, sir.